Hello and welcome to Little Big Physics, a series in which we try to figure out the mechanics of the world of Little Big Planet from the ground up. Last time, we began our investigation into how a push on an object affected its motion. However, somebody has posed a question that I hinted at in that same video. Does air resistance have a substantial effect on a slow-moving object like the ones we used in our tests? We know that air resistance exists, but the catch was that we don't know yet if using an anti-gravity modifier affects it. Anti-gravity modifiers have a property called damping that can be set anywhere from 0 to 100%, where 0% produces no effect at all, and 100% prevents the object from moving at all. At least, that's what it seems like. Between these two extremes, higher percentages result in the object slowing down much more quickly as it moves through the air, and lower percentages result in the object slowing down much more slowly. Since that seems to be what air resistance is, could it be that setting the damping to 0 negates air resistance entirely? If so, that would be an incredibly helpful tool for us in testing. To make this a bit less dry and more easy to imagine, here's a hypothetical scenario that depends on the answer to our question. On one side of a level is a bomb with an anti-gravity modifier at 0% damping, floating to the right at a snail's pace. All the way on the other side is an ill-fated sack boy, directly in the bomb's path. Will the bomb reach the unfortunate sack, or will it succumb to air resistance and stop before reaching its target? We'll use a pretty straightforward setup to test this idea. Using our graphing apparatus again, we can measure the distance traveled by a small block with an anti-gravity modifier over time. We'll give the block its initial speed using an emitter, which will emit the block with a speed of 1 length per second. Then, all we have to do is look at the graph. If the block experiences no air resistance, its graph should be a straight line, because it will move at a constant speed without air resistance impeding it. If it does experience air resistance, the graph should be a curve that never goes above a certain distance, because the block will slow down and eventually stop, in theory. So, what do we get? The block slows down over time, producing a curved graph. We've demonstrated beyond doubt, then, that objects with anti-gravity modifiers still experience air resistance. Out of curiosity, let's take a brief look at just how quickly the block slows down, too, since this is the first time we've seen air resistance alone acting on an object in the absence of anything else that might affect its motion, namely gravity. Was it a mistake for us to ignore air resistance in the last video? This whole graph is over the course of 30 seconds, and the dots are 0.3 seconds apart. If you look at only the first 7, or the first 2.1 seconds, the dots actually look remarkably like a straight line, as if the block wasn't slowing down almost at all. If the block had moved at a constant 1 length per second without ever slowing down, it would have traveled 2.1 lengths in that time, but it traveled closer to 1.95 lengths according to our graph, or somewhere around 93% as far as it would have theoretically traveled without air resistance. To be perfectly honest, that's a bigger difference than I was hoping for, but it's still small. Recall that we worked in intervals of 1 and 2 seconds in the previous video. Over 2 seconds instead of 2.1 seconds, a rough estimate is that the block would have traveled about 95% of its unimpeded distance, since air resistance wouldn't have been acting on the block for as long. Thus, based off of what we can see here, the experiment we ran last episode probably had about a 5% margin of error for each 2-second interval that we examined. Over only a 1-second interval, the travel distance is probably closer to 98% of the unimpeded travel distance, for a margin of error closer to 2%. In fact, remember how we calculated the final speed of the rocket block last episode, using the linear fit for the earlier 2-second interval while the rocket was off? The rocket was on for 1 second afterwards, after which the speed of the block was about 17 lengths per second. We calculated 17.37 lengths per second when we ignored air resistance. That gives us a margin of error of just over 2%, just like we predicted. We've answered our questions now. For instance, the unfortunate sack is safe and will not get blown up by the traveling bomb. But since this is the first time we've seen air resistance acting on an object in the absence of any other force, I think it would be a good idea to produce a fit for this graph, just to get an idea of what the mathematical model of air resistance might look like. Even though we're working with an object slowing to a stop, this might actually bear some resemblance to the equation that we produced to model a falling object. The only real differences are that there's no downward pull anymore, and the line that the graph eventually becomes will be completely horizontal instead of slanted downwards. Here's the general equation we found for a falling object. You might remember that c determines the slant of the line, which we just set as 0, so our model for the object in zero gravity will be of this form. Fortunately, we'll also be able to produce fits for this more easily in Microsoft Excel, or at least I think so. It would have been interesting to graph the same block both falling and slowing to a stop in zero gravity now that I think about it, but that unfortunately didn't occur to me while I ran this test. We might try that in the future though. That unfortunately means that we have nothing to compare this particular trial to, so I think I'll save myself more than an hour's work of producing an actual fit for this graph, since we already have reason to be confident about its general form. But just to be slightly more thorough, we know that b has to be a negative value, just like last time, so that the graph will eventually become a line. Furthermore, the sign of a depends on which direction the object is moving initially, positive if it's moving in the positive direction, right in this case, and negative if it's moving in the negative direction, left in this case. And, like before, d just shifts the whole graph up and down, so that can be pretty much anything as well. Well, I think today was a nice brief double check of something that we had taken for granted in the previous video. Just by challenging a single assumption, we got to learn more about one of the interactions that, as far as we can tell right now, affects everything we do in Little Big Planet. Now, though, I think we'll move on to testing out more new concepts to see what we can cover, to see if anything surprises us. Until next time, and stay curious.